I have a profound pleasure of being able to introduce to you, if you have not already met them, two significant leaders at Intel Corporation, Gadi Singer and Al Gara. To give some background, Gadi is vice president in our artificial intelligence group, but over years, he's designed seven different Intel microarchitectures designed and led. So quite a bit of background into, including architectures specifically for high-performance computing, and as well as now artificial intelligence. And Al Gara, Intel fellow, and one of my co-staff members. We work in the same organization. Al, I don't know about 7 different microarchitectures, but it's odd. I was touring Columbia University a couple of years ago, and they opened up a filing cabinet and pulled out a server board full of ASICs. 144-pin quad flat packs that had been hand soldered down onto the board. It was the first QCD machine, and I think Al did that while he was a postdoc at Columbia. So a long heritage of hardware, software, machine architecture, both at Intel and going back into experimental days, will be here for you in our next talks. The conversation will be about how HPC and AI have intertwined futures. I'd like to start by introducing and welcoming to the stage Gadi Singer.
Right, good morning. And today we're going to talk about two great disciplines, HPC and artificial intelligence, and how by working together between them, we are expecting some amazing things to happen. And I want to start with the artificial intelligence, and artificial intelligence is happening. And I trust your natural intelligence, so I don't need to prove that it is happening indeed and coming of age, but I do want to point out the pace in which it happens. If you compare where AI and our understanding and our solutions were as an industry 5 years ago to today, it's really a remarkable progress. And the fact that today we have autonomous driving cars that are roaming the streets, and there are medical scans where you can identify some malignant tissue at very early stage, and there are phones that can understand even my speech. So this is truly a remarkable progress over a short period. But this fast pace is not ending now. And it's important because the same rapid clip of change is coming into multiple industries. It is going to be difficult to find an industry that is not impacted by the technologies of artificial intelligence. Actually, not only impacted, it's going to be difficult to find an industry that is not transformed, changed in some fundamental way by the technologies of artificial intelligence. And you can see some of the concrete examples in each of those, but you can find in your own industry where you're working how the promise, the opportunity of AI is going to make this fundamental change. And we'll talk about how this is going to be done by the combination of HPC and AI. And before I dive into that, just a little bit of terminology. Some people use the terms interchangeably. I hope none in this audience, but just to set the stage, we're talking about artificial intelligence as the overall space. Within it, we have machine learning, which is about capabilities that are improving with time and with data. So rather than programming the final solution, you program the ability to learn from data and improve over time. And it has multiple branches in it, which are providing value, like SVM or associative learning. But I want to focus at least part of the presentation on one of those branches, which is very prominent and has made great strides, which is deep learning. This branch, which is relying on multi-layer neural network topology to ingest significant amounts of data and identify, characterize, and work with them. So with that, let's put them side by side. On the left, you have AI, and in the next few slides, I'll focus on deep learning. And if you look at what AI does, it's really about knowledge discovery. It's about taking very large volumes of data and being able to identify structure, identify patterns, It's about looking at multi-dimensional, n-dimensional space and identify clusters within that. So the how, the strong capabilities that are underlying deep learning are pattern classification, are about clustering, identifying classes within that, about feature learning, so identifying within a large space, self-learning of features, and anomaly. When you have a set of capabilities that are very good in identifying patterns, they are also very good in identifying elements that are close to the pattern, but are really different in some manner. And if you look at HPC as a discipline, which you're all very familiar with, about scientific applications and analytics at large scale, there are traditional, very important set of usages, a very large set of usages. I just gave a few examples here with climate and genomics sequencing, seismic, fraud detection. But the underlying how, the architecture, the infrastructure of HPC is mastering aggregation and scale, mastering the highest performance compute system, mastering massive memory structure, ability to provide the highest bandwidth and throughput. So those two disciplines, which are appearing here side by side, actually are having more and more reliance on each other. And I'll start with AI on HPC. If you look at the tasks of AI, they can benefit substantially from riding on the infrastructure of HPC. This is what can give them, and already starts to give them, the performance and the scale to solve the real large problems. And I'll talk about that in a minute. And at the same time, if you look at HPC, take the traditional usages of HPC and use AI as another tool in the toolbox, a very important and capable tool in the toolbox to create new capabilities for what are the usages of HPC. So let's dive into both of those, and let's start with running AI usages, AI applications on HPC infrastructure. What HPC infrastructure brings to AI is scale. All AI is about data, lots of data. But lots of data requires the compute and the memory systems in order to be able to scale. And for the real large problems, you have to have an HPC infrastructure in order to manage and in order to reach the required performance when you have very large data sets, when you have large batch sizes, which is how many of those cases are coming at once. And HPC's ability to effectively aggregate thousands of nodes to create an overall task is crucial for achieving scale with AI. And I really recommend that you come to the morning session, to the plenary session tomorrow with Pranav, and there are some great examples. This is the session about artificial intelligence in science. There are some great examples done with the Lawrence Berkeley labs that shows how you can take the large scales of HPC. This is just an example that I bring, reaching 15 petaflops by having a machine that has 9,600 nodes that are working together in concert to solve global climate maps. So this you cannot do without the scale and the power of HPC, and without, and you will hear tomorrow, without the technologies that are applied from the field of AI. Now there's another advantage. When we are developing an AI solution, there's a phase that has iteration between a data scientist or somebody that's working with the model and running the compute, the training. And having fast iteration, having the ability to examine, to explore and examine option is what determines time to train, which is a very critical factor for being able to be competitive, to achieve solutions. By having the performance and scale of HPC, we can have those iterations faster, have it as an effective process that reach the discovery that can be done with AI. So AI can build on HPC for scale and for fast iteration. But You are the HPC in your space. You understand the challenges and the opportunity of HPC, and the question for you is, how can I use AI and deep learning in particular to solve my problem, to provide some new solutions? And whether it's fluid dynamics or any of the other topics, I would say, and there are significant results already in the field, that by applying this, in addition to your favorite simulation and modeling and others, so you can still run Monte Carlo algorithms. This is not replacing all of that, but it is an additional capability that allows you to deal with spaces that are very large, that are changing quickly. So when you have an area like in fintech, where the trends are changing very quickly, you don't always have all the equations, all the complex and complete model to do all of that. You can apply the deep learning capabilities to learn those patterns, to be able to shift with those patterns, to identify anomalies to those patterns. And you use this great match between the underlying capabilities of AI to solve those problems, to create really breakthrough solutions. And breakthrough at the highest and the lowest, meaning the highest, take those large challenges in astronomy and others, and be able to use the compute capability together with the DL capability. But when you look at the other end, personalized, things like precision medicine, where you're able to take larger solutions, you take the inputs from particular individuals and be able to tailor solutions for individuals. So from the largest problems to applying large capabilities into individual problems, using deep learning in HPC has great promise for the future. And I want to talk about 5 transitions, because you're looking at a horizon that's out there, not what is happening in 2017. So I would offer that there are 5 major transitions that are happening in this space. And I'll start with the adoption of DL and deep learning and AI in general as an HPC capability, as a tool, major tool in the toolbox. Today, it's already being adopted, but I would say that in the adoption model is probably early adopters. You can see results, but really a lot of HPC is still using more tried and traditional techniques. But I can see that changing very quickly in this 3 to 5 year horizon. And it is going to change quickly, because unlike some of the traditional practices where you have to have programmers that tease out the parallelism in a solution and map it to multiple nodes, deep learning has the ability, once you create the right models at the deep learning framework, to automatically extract this massive parallelism into the hardware. So you need to build the right models on top, but really using all those nodes is done by the mapping of this layer down to whatever hardware construct you have. So I expect that within 3 to 5 years, 50% or more of the applicable usages will be using effectively deep learning. The other point is that from recognition, which is identifying images, identifying something in medical, will go to understanding, which is a much broader scope. When you look at recognition, usually you have very dense information, rather local. Understanding in your brain, in the way it's done, it's much broader. It needs different memory structure. So this is an example. This is the 6-word essay by Hemingway. Recognizing the words is very different level than understanding what we as humans understand the meaning of this. And this is one of the phases going to understanding. Another major transition is the shift from diagnostics, which is what is usually done today, to predictive, to prescriptive, and generative. So within 5 years, we will have deep learning architectures that are using like GANs, generative adversary networks, or others, to predict, but also to be able to generate new behaviors. So in terms of prediction, if you're doing climate change, it's important to know that there's a hurricane forming, but it's kind of important for some people to know if it's going to hit the east coast of Florida or the west coast of Florida. And beyond that, in generative, maybe not in climate yet, but in other systems, to create actions that changes, not only predict what's going to happen. The fourth trend is scale. AI is going to ride the transition that overall HPC is doing to exascale. And Al, who's going to come after me, is going to talk about that and going to talk more about the technologies and capabilities of the journey to exascale. And the fifth trend deserves its own slide. Due to the importance and the prevalence of deep learning, we can see an emerging trend of machines that are targeted for deep learning, training, and inference. And this is a new class of machines. And to create this, there needs to be a rethinking of all aspects of compute, the compute elements themselves, the memory, the interconnect. So we need to have things like tensors as a native data type. Spatial processing, which means it's not instruction pointer based. It's a very wide front of processing that goes through a wide set of compute elements. Having the specialized memory and the memory hierarchy, you don't want to compete in cache. You want to have enough memory on die to bring all the layers that are required in and other aspects. You need to have very fast connectivity, interconnect, and have tight software control. And all of those elements we're going to talk about in a minute in actual products. And let me be clear, those are not GPUs. GPUs are being used today, as are CPUs, but they do not possess all those unique architectural characteristics, and therefore they should not be called DLAs. So true DLAs, dedicated deep learning accelerators, promise to have significant benefits in terms of their performance and power efficiency. And of course, as part of a larger solution, we need to have those highly specialized engines together with general purpose like a CPU to provide the full end-to-end solution. And this is a good point to transition to what Intel is doing about it, because Intel has a very unique lineup of capabilities in this space. And of course, in the center of the picture, you have Xeon, and we also have Xeon Phi, of course. And this is really the foundation. The large majority of AI cycles run today on those machines, on those architectures, general AI and others. And the scalability and versatility allows those machines to get you into the AI space. And Intel is adding specialized instructions in the ISA, in the instruction set architecture, to help do that even better. For more specialized architecture, you see on the left the FPGA product line with Stratix 10 that allow you to solve some workloads very well, especially when they are latency dependent and others. And on the right, you have a true deep learning architecture, which is added to the lineup, which is the Nirvana Neural Network Processor, or NNP. And we're talking more and more about that in the coming weeks or months. We'll add more details in NIPS and in other occasions. But just to give an overall view of this architecture, this was designed from scratch as part of Nirvana. And as of last year, it's part of Intel. And really looking at all the elements that are required to provide optimal performance. So parallelism. We have massively parallel compute elements, lots of compute elements with linear algebra, with specialized instructions around convolution and matrix multiplication and activation functions, and they are laid out in a way that they can access very effectively. There are fabrics that allow data to move directly to those from memory and between compute elements. And there's optimized numerics, the flex point, that allows a much higher efficiency in dealing with large number of operations. In terms of scalability, there's scalability that is happening by the right structure on die, like having enough memory, having the right access to memory, but also between dies, having fast interconnect, which is very important to memory, but is also very important in die-to-die connectivity that allows scaling, as you guys know how to do very well. Utilization. Of course, talking about peak tops, teraops is important, but what really delivers the work is the effective compute that we have, which is utilization. And there are some unique capabilities that you can put, because unlike general purpose compute for human machines, here you know what's going to happen. You can plan in advance, and you can control the flow of data between memory, the compute elements, more compute elements, back. You can plan and control it in a way that gives you optimal use of the assets that you have on the die. And in terms of roadmap, when Nirvana joined Intel last year, we put together a very aggressive roadmap on how to increase both performance and power efficiency, and we have the roadmap and the development in place to meet the goals that we have set. But we looked at the individual element. Of course, a solution has to provide a much broader space. And this is where Intel, again, is providing a very unique breadth as well as depth, or if you'd like, height of the solution. So in terms of hardware, this is a very unique set, a unique portfolio of hardware components. We talked about some of them, the Xeon, Xeon Phi, the FPGA, the DLA, but there are also other elements that allow end-to-end solutions, such as the networking, the memory, the storage component that come from Intel and are being designed to work well together. And other elements of end-to-end solution to the edge, like the Movidius acceleration and others. So a portfolio, a wide portfolio of hardware assets. But on top of it, you have the libraries. This is important in all hardware, but especially in accelerators, to have the right libraries. They can take from basic primitives, if you look at the DNN primitives or other primitives, and map it down to whatever hardware assets you have, using the best hardware. If it's a Xeon-only system, or if it's a Xeon integrated with an NNP, how to map those primitives to the best hardware. And an asset such as the Nirvana graph. Nirvana graph is connecting to all the popular deep learning frameworks, and I'm sure you can find your favorite framework in here, and doing the hardware-independent processing of the graph. And then from that is mapping to the libraries and to the particular hardware. So you really have a funnel from all those front ends of frameworks onto an optimization point and onto the hardware that you deploy at that time. And on top of that, you have a set of tools that allow progressing on AI capabilities faster. And whether it's the Nirvana Cloud, the Deep Learning Studio, or the SDK, all those are addressing what I spoke about earlier, the time to train. How do you give the tools to observe, to create the iterations, to provide the support to the top layer, which is what we all care about? Those are the solutions and the experiences. So this has been a tremendous growth over the last 3 to 5 years, but it's now blossoming, and we're going to see major transitions into the exascale use of HPC for AI at a large scale, and the evolution of the AI capabilities to solve HPC solutions, to add this flexibility, this recognizing that is so helpful in those. And together, this combination of discipline is going to bring breakthroughs at all levels of the solution space, both in terms of identifying the opportunities and creating things that will only be able to know how far they can go when we get there.